All right, friends. Happy Friday to all of you. Welcome back. A common question at this point in the course is, oh my goodness, there's so many reactions. How do I keep it all straight? It's been a whirlwind, and I'm sure you feel like every day you come in and there's just more stuff. And that's why we spent the first half of the semester teaching you the language of organic chemistry to build the skills so that you could handle the new reactions. But I sense a disturbance in the force that there's some anxiety about, well, have I got all the reactions? Am I going to miss any? And I want to be like Darth Sidious and tell you that your anxiety gives you focus, makes you strong. But instead, I will tell you that there are some resources for keeping track of the reactions. Of course, they're all in the notes, so there's nothing secret or surprised. But you can go to the content page of Learning Suite, and there are some handouts listed that summarize the reactions that we talked about for each chapter. Now, I mean, sure, yes, all right, thank you. I don't know that you'll find them useful, any more useful than the end of chapter summaries, but if you click on one, it will show you stuff. Yes. Now, all of that was in your notes. But I know that you're scrambling and worried that you've maybe missed something. One thing I will tell you, this is kind of important. These handouts are somewhat old and I haven't revised them recently. So anything I tell you in class about what you need to know supersedes what's on here. Let me give you a brief example of that. The Sockle mechanism or the Sockle reaction, I told you in class, don't worry about how Sockle turns OH into a good leaving group, but do know that having done so, Cl- comes in from the backside and does SN2 to get rid of that good leaving group, and that gives you the alkyl halide, right? We talked about that. You do need to know that SN2 mechanism. There's some details here. That part is included, right? Cl- displaces the Lg leaving group in an SN2 mechanism. We observe inversion of configuration. But there's some stuff here about how it turns it into a good leaving group, and there's some stuff about what happens to the leaving group after it leaves that you don't need to know. So pay attention to what I've said in class. If you'd like me to say it all again, that's okay. You can go to YouTube and watch the video where I say it all again. But anyway, what I've said in class supersedes mechanistic details that are on this. And I think most of the time you're going to be okay. But if you see a detail, and I've told you don't worry about that mechanism in class, what I say in class supersedes it. As I said, I think it's all mostly good. But you'll see this both for chapter 9 and chapter 10. And then there's one for chapter 11 as well, which we haven't got to yet. The one thing from chapter 10 that's not on this is the alkyne stuff. And we did that really briefly at the end of class last time. I did this because these are reactions that when you take 352, they'll probably expect that you know. And I also did it because it's not that much of a stretch from the alkene, corresponding alkene reactions. This one here is alkene hydration under acidic conditions. It's called hydration because the things that you add are H and OH, which is water. That's why it's called hydration. The one up here is called hydroboration oxidation. You can remember that because boron is involved. And like alkene hydration, you're adding H and OH in place of one of the pi bonds of the alkyne. It functions exactly like alkene hydration or alkene hydroboration oxidation in that the OH for alkyne hydration ends up on the more substituted carbon, and the OH for alkyne hydroboration ends up on the less substituted carbon. That's exactly the same as for the alkene chemistry. The difference is you've got 2 pi bonds instead of 1. One of the pi bonds reacts, the other is still there, and that is why your product in both cases is an enol. Only for hydroboration oxidation, the oxygen of the enol is on the less substituted carbon, whereas for hydration it's on the more substituted carbon. Now the thing I added last time was that the enol is a less stable isomer of an aldehyde or a ketone. We talked about the enol form versus the keto form, and we said the keto form was more stable. The reason for that is that carbon-oxygen pi bonds are way more stable than carbon-carbon pi bonds. So it's more favorable to undergo this process, which we called tautomerization. Tautomer is a word that describes isomers that differ only in the location of a pi bond and a proton. And tautomerizing or tautomerization is the word we use to describe the process of converting from one tautomer to another, moving a pi bond and moving a proton. I showed you that process last time, but it was towards the end of class, and I assume that some of you didn't quite get it down, so I wanted to talk about it again. Tautomerization, as I said, happens because it gets you from the less stable enol form of a product to the more stable keto form. That's the driving force. So that's why. How is an issue of mechanism, and it can happen in one of 2 ways. It can happen under basic conditions or under acidic conditions with similar efficiency. And that means that even in pH 7 water, an enol will tautomerize to the more stable keto form. So you don't need to worry about how do I know if the enol is going to tautomerize. It will. Whether you're under acidic or basic conditions or even in neutral water, it will tautomerize. Here's how that process happens. You will notice that tautomerization mechanisms involve simply proton transfer steps. The only thing that's changing here is where protons are. So, under basic conditions, OH minus deprotonates the enol. You get to the conjugate base of the enol that's called an enolate. I'm going to just ask you to put the word enolate on a drawer in your mind's filing cabinet or a room in your mind palace if you have one. I've tried to construct one and it didn't go very well. Put a room in there for enolate because enolate's going to be really important in 352. One important thing of the enolate that you can understand already is the fact that the negative charge on the oxygen is delocalized by resonance because of that pi bond. And the negative charge can either be on the oxygen or on the adjacent carbon. And if you protonate on the adjacent carbon, you get the more stable keto form, which in this case is an aldehyde. It's an aldehyde because the oxygen of the enol was on the less substituted carbon. If you want, you can also show this mechanism from this resonance structure of the enolate. It just looks like electrons kick down to form a pi bond between oxygen and carbon B, and then carbon A picks up a proton as these pi electrons move over onto carbon A, and we steal a proton from water. All right, that's the basic tautomerization mechanism. Go ahead.
Why is it that B gets the proton
Why is it that, I think you're asking back at the stage of here? No?
No, yeah, it shows.
Sorry.
In the mechanism, it shows first that the lone pairs on that oxygen is gathering the double bond, and then it acquires that proton. That proton goes on carbon B, and then later.
No, it actually, so yeah, that's the misconception here. This arrow is showing the pi bond between O and carbon B. This arrow here means carbon A is getting the proton. Carbon B can't get the proton, it would have too many bonds.
Okay, where's the proton on? If it's positively charged.
Sorry, say that again?
Where's the proton on A?
It's possible that you're viewing this as going to here. Those are two different resonance structures. This one goes directly to here. The proton that we add is coming from water. Okay. Yep. Others? Yeah.
So either resonance structure gets you the same.
Either resonance structure gets you to the same place. I'm showing you how to draw the mechanism from either resonance structure. Just pick one and you're good. All right. So under acidic conditions, the mechanism is similar, except the order of the proton transfers is a little bit different. So we start under acidic conditions by having the electrons in the pi bond between A and B attack a hydrogen from H3O+. That's basically exactly the same first step as we've done with adding acids to alkenes already. You're going to put that proton from H3O+ on the more substituted, you're going to put that proton from H3O+ on the less substituted carbon so that the positive charge can be on the more substituted carbon. And it gets even better than that because the lone pairs on the oxygen can stabilize that positive charge by resonance. If they kick down here to form a pi bond, you get this resonance structure. To convert fully to the keto form, you can do that from the resonance structure on the right simply by having water remove a proton from the positively charged oxygen. Or if you wanted to do it from the resonance structure on the left, you would have water remove a proton from the oxygen and electrons kick down to form a pi bond. The option on the right looks just like acid-base chemistry. The option on the left looks kind of like E1 chemistry, removing a proton that is beta to a positive charge. Either of them are okay, and in this case, the keto form is a ketone. Why is it a ketone? Because the oxygen was on more substituted carbon A. All right, so I do want you to know that. If you print out that handout from chapter 10, add these two reactions to it. And make sure you know the mechanism of tautomerization. I'm doing that now because some of you aren't going to have me for 352 in the winter. I'm going to teach it again in 352, but your 352 instructor might expect you to already know it. So I want to make sure that you're prepared for the future. Okay, any more questions there? Go ahead.
So for it to tautomerize within acidic conditions, would it have to be on the more substituted side?
Right, so the question is for stuff to happen under acidic conditions. You're noticing that I changed where the OH group was under basic or acidic conditions. That was just to follow the conditions of the reaction. Notice that hydroboration oxidation is under basic conditions. Alkyne hydration is under acidic conditions. So I was just using these enols, but actually any enol can tautomerize under either acidic or basic conditions. Yeah.
So does this apply to like any of the reactions? Like how do we distinguish what an enol is and when it can For
Okay.
these two reactions?
So an enol specifically is an OH on a vinyl carbon that's involved in a pi bond. This is the first enol you've seen. If you go back and look at all the alkene reactions, none of them gave you enols as products, which is why we didn't talk about tautomerization until now. Did I see another hand? No? Okay. Well, now I want to spend, and we'll probably spend most of the rest of our time today on synthesis. Dun, dun, dun. And synthesis is using a series of reactions to build a molecule of greater complexity than the one you started with. And it's synthesis in more than one way, because doing chemical synthesis requires you to bring together or synthesize multiple concepts at once. Punny, yes, thank you. One of you, yeah. So let me give you an example of why you would want to make a more complicated molecule. Behold the chemical paclitaxel. This is a molecule that's marketed as a drug called Taxol, and it's used for treating cancer, including breast cancer. And years ago, this was one of the few effective treatments for breast cancer. It was isolated in 1971 from the bark of the yew tree. Now, when you find a molecule, and often scientists do this, it's called natural products isolation. You go to some strange location, you gather leaves or bark or some essential oil, or you go diving and you gather a marine sponge and grind it up and try to isolate the molecules that come out of it. And there are often very interesting, complicated, unusual molecules that you can isolate from these natural sources. And you're like, why on earth is that organism making this thing? And people try to research that. But some of these molecules that you can isolate from natural sources have interesting properties, like they'll kill cancer cells. So this is an example of one of them. The issue was that you can't get enough of it. There weren't enough Pacific yew trees in the world to grind up all the bark in them, isolate paclitaxel or Taxol, and then give it to all the people that had breast cancer. So enter the chemist that's like, I bet I can make that. Now, you're looking at that and you're thinking, ain't no way. But actually, chemists can do it. And that's why this is an introductory class in OChem. I actually don't know how to make paclitaxel, but Dr. Castle and Dr. Andrus and Dr. Michaelis certainly do, because their specialties in total synthesis. Yeah?
How do you even know if you successfully made it? Like, you can't obviously see.
That is a great question, because we can't see atoms. So how do you know if you've successfully made it? Stay tuned. We're going to talk about a few analytical chemistry techniques that we can use to prove that we've made the thing. Yep. So stay tuned. We won't do anything this complicated, but you'll learn that. So what do? The chemist says, I can make that, and develops a synthesis. Now, when you see something this complicated, it's difficult to know where to begin. The decision about where to begin a synthesis is essentially an economic one, and it's a supply chain one. It's like, how am I going to get enough of a starting material at the right price so that I can make this molecule and sell it and still make a profit? And so you have to decide, okay, what's my starting material going to be? For our purposes, when we do a synthesis, I'm going to tell you what the starting material is. And if you were actually working from a company, you could choose whatever starting material met your economic needs and gave you the best synthesis possible. For our purposes, I'm just going to tell you where we have to begin, and you'll see where to end up. Now, often, if you start at the beginning, there are so many different ways to start that it's difficult to choose one among the many possible options. But often with complicated molecules, there's not that many ways to do the final step. And so it's often more efficient when you're thinking about a synthesis to plan it in the reverse direction. That is, you start at the end. President Nelson used to say we're going to begin with the end in mind. That's what we're doing here. You start at the end. You think, what do I think the last reaction was? And then you take a step backwards. And that's called total synthesis. So we're going to do that with this simple case. Now you're looking at that, you're thinking, oh, see, if I had showed you this first, you'd have been like, no. But now that you've seen paclitaxel, you're like, okay, well, at least we're not doing that, right? So this problem is formatted in an open-ended way. It says, make this target molecule. Why on earth would you want to make it? We're going to pretend that it has some desired property, like it kills cancer cells, or it lures wasps to their doom, or something like that. Okay, target molecule, and then here is allowed starting materials. Now, why are they allowed starting materials? We're going to assume that somebody did the analysis and that's all our company can afford. So that's where we got to begin. Now, you're free to use any other reagents, but all of the carbons in your product have to come from those allowed starting materials. The process of thinking backwards, planning a synthesis in reverse, is called retrosynthesis. That doesn't mean that what for you guys, retro is what? The 1990s? Maybe, no, even the early 2000s. Anyway, yes, well, retro here just means backwards. So the first rule of retrosynthesis is focus on carbon-carbon bonds, because those are the steps, and I'm talking about carbon-carbon sigma bonds mostly. Those are the steps where you build up complexity from smaller things to larger things. So if we look at our target molecule, it's got 6 carbons. 1, 2, 3, 4, 5, 6. Hopefully by now you're getting used to how we draw alkynes and you know that there is a carbon there and a carbon there. 6 carbons. If you look at the allowed starting materials, they only have 2 carbons. Now, one of our goals in synthesis is efficiency. So we don't want to reinvent the wheel or do anything that we don't have to do. So if you notice in these starting materials, I already have a bond between 2 carbons. So I want to keep that bond, that sigma bond between 2 carbons as I make my final product. In other words, I don't want to reinvent the wheel and decide, okay, actually first we're going to cut that up into really small pieces and then we're going to stitch them all back together. You could probably do that, but it would be boneheaded. Nobody in their right mind would do that. It would be a waste of money. So play to your strengths. Use the sigma bonds you already have. Use the carbon-carbon sigma bonds you already have. And then figure out which ones you had to have made. So if I look at the product, I can see that 6 carbons divides neatly into 3 2-carbon chunks. In other words, those 2 carbons, those 2 carbons, and those 2 carbons, which tells me that sometime along the way, I had to make the bond between carbon 5 and 4, and I also had to make the bond between carbon 2 and 3. Do you follow that reasoning? Any other strategy would require me to take a 2-carbon starting material and cut it up into 1-carbon pieces. And if I don't have to, then why would I? It's going to be more efficient this way. All right, questions about that? Okay. So now once you've identified the bonds that you have to have made, the second thing you want to do is pay attention to structural patterns. So the first structural pattern to pay attention to is, what kind of sigma bond, carbon-carbon sigma bond is this? And one thing that'll help is to notice that it is a sigma bond between an sp carbon with an adjacent sp3 carbon. Then you start to go back in your mind and try to think of reactions that you've seen before where you made this kind of bond. This is where familiarity with the reactions will not be enough. This is where you need to have actually mastered the reactions. Because many of you, if I give you a nucleophile and something with a leaving group, you're like, oh, that's a substitution reaction, that's great. But fewer of you can start here with a product and think backwards to what the starting material and the reagent could have been. I told you about flashcards where you were going to do starting material and reagent and then what the product is, starting material and product, guess what the reagent is, and then product and reagent, guess what the starting material is. All of that's preparation for synthesis, and it's really preparation to get you here. This is the boss level flashcard where you're given a starting product but not the starting material or the reagent, and you got to provide both. If you can get to this level and do it well, you'll be well prepared to do synthesis. So let me just ask the question, can anybody think of a reaction that we've done before that makes a bond? And before I ask the question, you got to relax your eyes a little bit, not be so worried about making this specific molecule, but just generally, we're just planning out a strategy here. Can anybody think of a reaction we've done before where we made a bond between an alkyne carbon, sp hybridized, and then an adjacent sp3 carbon? Yeah, go ahead.
It's the one, I don't remember what the name is, but it's the one where you have like a anion.
Okay.
So, like where it starts with a normal alkyne and you protonate it with a strong acid.
Okay.
And then you can attach other stuff.
So you're thinking, and we're going to just be general with R, it could be H or something else, but you're thinking of, this is called an acetylide anion. And then, so that's going to be your nucleophile. And then what are you going to react that with?
Any, like whatever electrophile you want.
Okay, so any electrophile you want, good. Propose one that might make this bond.
Someone else's turn.
Someone else's turn, good. Okay, you want 2 carbons, like ethyl, and then what else? What else would I need to do? I would need some kind of leaving group, right? Okay, so, and a convenient leaving group might be a halogen, like Br or Cl. Now, remember, as I'm thinking backwards, I'm suspending disbelief because your mind is going to say, you didn't start with one of these starting materials. And I'm going to be like, no, don't worry about that. We're going to make these simpler starting materials from these. We're just thinking about the first backward step. This is like a Russian nesting doll where there's new problems inside to be solved all the way back. So it's okay. Oh no, where did it all go? I was trying to circle things and suddenly it was an eraser. There we go. Don't you wish life had an undo button? That would be really great. It does. It's called repentance. That's your spiritual message for today. Okay, so yes, this is a good strategy for making a bond with an adjacent carbon. This is an SN2 type reaction, and that will make a bond between an sp hybridized carbon, and an adjacent sp3 hybridized carbon. So I propose that this is a good strategy for making the carbon-carbon bond between carbons 4 and 5. Now we haven't totally worked it out yet, but this is the planning stage. This is the spiritual creation of our synthesis. We're not worried about it making sense from start to end. What we want to know is this an actual reaction we've done before? Is it a sound strategy? And yeah, looks great. What about the bond between 2 and 3? That's also a bond between an sp3 carbon and an sp carbon. The difference is you've got an OH over here, whereas over here there was no OH. Okay, any ideas, strategies for making the bond between 2 and 3? I heard something. What was, somebody was muttering something out there. You want to, could use the epoxide as what?
As electrophile.
Okay, as electrophile.
On the other side, they said it would also be a hydrogen that you could then deprotonate, give it a negative charge.
So you're thinking if I had an acetylide ion like this, and I use that as my nucleophile, and then the epoxide as an electrophile, that's SN2 epoxide opening. That's a reaction that we've done before. You may not have thought to use an alkyne before to open up an epoxide, but that works. And that would give us this product, a new sigma bond with the carbon of the epoxide, and then on the adjacent carbon you'd have a negatively charged oxygen, which we would protonate in a subsequent aqueous workup step, probably to give us the alcohol. Okay, good. Now, if that didn't occur to you, one of the things that will help when you're doing your flashcards is to pay attention to structural patterns. Notice that the product of this reaction has an OH group from your epoxide and then the nucleophile, and they are on adjacent carbons. You have this sort of 1-2 substitution pattern, 1-2 nucleophile OH pattern. And you can see that that pattern is present in the product. If you look for structural patterns and start to master them, you'll be able to look at a product like this and say, oh, hey, this could have been an acetylide nucleophile. This could have been an epoxide. Why? Because the product is a 1-2 nucleophile OH pattern. So look for that. That can be a structural clue as to a reaction you can do. Okay, so we've got a plan now for those 2 sigma bonds. Now we need to think a little bit about strategy and order. Which one of these do you think we want to do first? I asked that at 8 a.m. Don't feel bad if you got nothing, because they had nothing either. Okay, first one, second one. Let's think about this. Ideally, you could start. We were generic about what the R was here. R could be either carbon or hydrogen. Ideally, before you do any of these reactions, your starting material is this, right? And presumably, and this is, by the way, this is the messy process of retrosynthesis. You think backwards a little bit, you think forwards a little bit, you try something, you see if it works, it doesn't. Some of you want the process to be, I want an algorithm that I can just load up in my mind and get the right answer from the very beginning and just never make any mistakes. And I'm sorry, folks, but this is not that class. The only way to do this is how I'm showing you, to think backwards, to try some things, to make mistakes, make adjustments. It's just like life. There's no way, man, we're getting spiritual insights all over the time today. There's no way to do life where you just load the algorithm and never make any mistakes. Or rather, there was a way to do that, but it was called Satan's plan. So we're not going to do Satan's plan for synthesis here. You're going to have to make mistakes, figure it out, retry some things. So, presumably, you remove the proton from the alkyne to turn it into a nucleophile. Now, the pKa for that proton is 25, so you need a strong base. One of the bases that is used commonly is NaNH2, where Na is plus, NH2 is minus. Alternatively, you can use NaH. Both of those are bases whose conjugate acids have pKa's greater than 25. So that's just acetylide deprotonation. Now, can you think of a problem with trying this? Suppose we tried to do the first, suppose we tried to do the 2,3 reaction first. That would have given us this product where we've got the alcohol, and then we still have a proton on our alkyne. And then suppose I try to use this base and I want to deprotonate the alkyne. What's the big problem? It's going to deprotonate the alcohol. All of a sudden, we're back to chapter 2. Which proton gets removed first? Write down the pKa's, 16 to 25. It's no contest, folks. Your base removes the proton from the alcohol, and you don't do what you want. So that tells you that we need to do this one last, so that by the time we get the alcohol, we never have to deprotonate an alkyne again. Do you see that strategic issue? Okay, good. So the plan will be then, and this is where we can start drawing out our retrosynthesis plan. Now that we're getting a sense, we can make it a little bit more formal. We said that the final step is going to be epoxide opening. That's going to be an SN2 reaction. Our starting materials will be the ethylene oxide, and then the nucleophile would be this acetylide anion. Now we're saying what that R group is. By the way, anytime in a synthesis you use as one of your allowed starting materials, you need to celebrate a little bit and say, yay, because, go ahead. Yay. Okay, that was enthusiastic. That's fine. Because we are now one step closer to the allowed starting materials. Some people, of course, you can get the acetylide anion by the deprotonation reaction. When I do a retrosynthesis, I write down as much about the reaction as I feel like I need to know what's going on. So alkyne deprotonation with, sometimes I'll even write the reagent down so that I know how to do this. Then, okay, where am I going to get that one? Notice this is the making the sigma bond between 2 and 3 step. Here is going to be making the sigma bond between 4 and 5. The precursor to that is going to be this acetylide anion and then this alkyl halide. Now, we got a problem, sort of, because this alkyl halide is not one of our allowed starting materials. But do you know of a reaction, thinking backwards, where we can take the OH group and turn it into the BR? Go ahead. Sure. So that's the HBr reaction from chapter 9. Alternatively, there was another one. If you didn't want to do that, what would you do? Hydration with water. That would go in this forward direction. Yeah, you could use OH minus as a nucleophile, but what if you wanted to go with the alcohol to this direction? You think if there's one more reagent from chapter 9? P starts phosphorus, PBr3. Nobody tries to pronounce that one. PBr3, PBr. Now we do, yeah. So, okay, and now we have, yay, gotten to another allowed starting material. Now we have to think, how do we make the alkyne? Of course, making that acetylide ion, we can do alkyne deprotonation, and that's going to get us here. So that's the last 2-carbon chunk we have to worry about. We've made the 2 carbon-carbon bonds. Now we have to figure out, where did we get that alkyne from? And it turns out there's a way to do this, but you may not have been paying attention to it, and you may not have noticed it, though it's, I think, been done on your problem set. Rather than have us think backwards through this one, I think I'll just show you how to get from the alcohol to the alkyne. But that's something you should work through on your own, because it's a really useful reaction series to have mastered. You can see that making the alkyne enables us to make a nucleophile that we can then use to make carbon-carbon bonds. So you can actually do this pretty easily. The first step, and now we're doing it in the forward direction, is alcohol dehydration with pocyl and pyridine, or if you wanted, you could use H2SO4. That would give you the alkene. Alternatively, if you wanted to go a little more slowly, you could use PBr3 or HBr to make the alkyl halide, and then you could do an E2 elimination reaction with tert butoxide. I can't remember what I've said to you versus the 8 a.m. class. Often there will be multiple routes possible for a synthesis. The standard is, does your chemistry work? Often, if you're the first lab in the world to synthesize something, you get to publish a really great paper in an awesome place, and people are like, hey, that's the first total synthesis of whatever cool molecule, how impressive. And then a couple years later, somebody comes along and says, I made it in fewer steps and better yield, neener, 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 and that's like the title of the, no, it's not, but in fewer steps and more efficient. And this is how organic chemists flex on each other, by counting steps of the reaction, counting overall yield. So if it were me, I would prefer to do this in 1 step instead of 2, but doing it in 2 steps is not wrong. Both of those options are right. If what I write on a key only shows one of those options, but you think your option works, then you're probably right if you're using chemistry that we've talked about. If you're inventing new reactions, you're probably wrong. But if you need to talk to me or a TA to compare your answer to the key, we're happy to help. From that alkyne, you can do a chapter, and you can do a chapter 10 reaction called alkene halogenation to get this molecule that's called the vicinal dihalide. And then you can use 2 equivalents of a very strong base, often NaNH2, to do 2 E2 reactions to make 2 pi bonds. That is something that was present in chapter 8, section 8.10 of chapter 8. If you don't remember that, go look at it again. It's a good strategy for making an alkyne. Some people, knowing that you're going to use the same base anyway to deprotonate the alkyne, go straight from the vicinal dihalide all the way to the acetylide by just saying, okay, I'm going to use 3 equivalents of base, 2 to make the alkyne and the 3rd to deprotonate. Okay? You follow? Yes?
What's the point of adding the Br to it? Why can't you just use the NH2 equivalents on the double bond?
The reason this works with the NH2, the question is, why make the Br? Why can't you just use this on the double bond? The base has to have a proton to remove and a leaving group to leave. What's going on in this step is literally base removes a proton and leaving group leaves. It's an E2 reaction. So you need to get the bromos there so you can have leaving groups. If they're not there, you can't make the pi bonds. Yeah.
So just to clarify, when we're talking about like allowed, initial start, like the starting materials, we can put whatever we want in there, but we can't put any like alkyne or alkanes in there, and like in that you have to get your carbons from.
Right. So the way the problem is formatted, and I'm really specific with the words. Every carbon in your product must come from one of these allowed starting materials. Other than that, use whatever reagents you want.
Okay.
Yeah. Okay. So we've now mapped it out. We have accounted for all of the carbons and all of the bonds in the product. Now your task is, and I'll leave this to you to do in your practice, is do this in the forward direction. I've already given you some of it in the forward direction. We've connected the dots all the way here, but after that they were just retrosynthetic arrows. So I want you to write out the synthesis in a nice way. This is going to take practice. This is hard. People come to my office and they say, I'm really struggling with synthesis, and I'm like, join the club. Everybody is. It's hard stuff. The only way you're going to get there is by putting in the reps to master the reactions so that you can stitch them together in this way. If you need practice, and I guarantee you that you do need practice on this, there'll be synthesis problems on problem sets from now on, but you can also go to the end of each chapter, chapters 9, 10, and 11, look at the practice problems, and there you will find synthesis. There will be a section called synthesis, and if you want to practice making stuff, then do some of those synthesis problems. Train on it, because the only way to get good at it is just to try and fail and try and fail and try again until you get it. All right. There was a question in the 8 o'clock hour that I feel like I should address, which was, how might this be tested on a multiple choice exam? If this were not a multiple choice exam, it would look exactly like this. It would be a blank sheet of paper with that on it, and you would do the synthesis. That's a really great exercise. It is a challenge for people to grade because there are so many potential ways to do it and so many potential ways to do it wrong that it's hard to assign partial credit in a way that's consistent across the class. And it takes a long time to grade, which means you don't get feedback very quickly. So how I format synthesis questions for multiple choice exams are, I show you the starting material, and I show you the product, and then we put a big question mark there, and then I give you options A through whatever, not C, it's going to be harder than that. Z, oh, okay. Yes, I like how you think, but no, there's not that many options. It'll usually be A through D or A through E, and each of these will be a box with a list of reactions, reagents, and so on. And only one of them will work, or sometimes two of them will work, and I'll ask you to choose the two that work, and not the ones that don't work. Now, you can approach this the way a lot of students want to do is they'll be like, okay, I'm just going to do this as a mini predict the products question. And then they proceed to look at it, do it in their head. Okay, I think that's it, and then they move on. If you're going to do that, you need to write out the product from each reaction and make sure that it works, because I will make it so that this list looks like it's going to work, but there will be a reagent that does something that doesn't give you the right stereochemistry or doesn't give you the right product. So don't do it in your head. And in fact, it'll work best if you actually plan out the synthesis on scratch paper first and then look at the answers to see what you think is going to work. All right. That's all we have time for today. So have a good weekend, and I will see you Monday.